This week we will discuss recent variants of stochastic gradient descent approach, which widely exploited for deep learning algorithm very recently. So let's consider this very simple 2D case. Here 2D means we have two input variable, let's say x1 and x2. And this round curve represents the contour having the same loss function value, and this zigzag trajectory represents the gradient descent path. When you compute gradient vector, then you can find this direction is the gradient descent direction, and since the curvature to x2 direction is more steeper than the curvature to the x1 direction with some large constant. Although the movement toward the x1 direction is very small, the movement or update length to the x2 direction with respect to x2 direction is very long, very high. So basically, although you move very little bit toward global optimal point, you have a very high movement to the x2 direction. So you basically move to here. And then again, when you come to the gradient descent, at this time, at this moment, you have complete opposite direction. And again, because the gradient with respect to x2 axis is much higher than the gradient with respect to x1 axis, you have very huge update to the x2 direction, but very tiny movement toward x1 direction. So you iteratively observe this behavior, and then you have this zigzag behavior. Basically, this kind of zigzag behavior is one main source of why your gradient descent algorithm converts to local optima very slowly. Okay, so basically, this happens when your alpha and beta is completely different. If your alpha is 0.1 and your beta is your beta is 10, then the beta over alpha is 100. And when you have a very high beta over alpha value, as we discussed earlier, the simple gradient descent algorithm cannot make very fast convergence. The running rate or update step size just depends on beta, so you have to set 1 over beta step size. But when beta is much higher than alpha, at some point to some direction, your update length, your learning rate 1 over beta is too small to go to your local optimal point. Okay, so when you have very different alpha and beta value, it is very hard to find a good step size to make a very fast convergence. Okay, and this kind of situation happens more often when you have high dimensional structure. And very recent machine learning algorithms, including many deep learning architecture, they have a lot of parameters, millions or billions parameters. So in that case, basically there are huge chance we have a very different alpha and beta, and it is very, very difficult to find a good learning rate.